Hello dear students, welcome to the series of Design of Machine Element lecture. It's a 25th lecture in the series and today we are going to discuss about design of helical compression spring. This is the third lecture on design of helical compression spring. In previous lecture we discussed about terminology and nomenclature of helical compression spring. In previous lecture we discussed about stresses developed in the helical compression spring. In today's lecture we are going to discuss about how to find out deflection in the helical compression spring, which plays very important role while designing the spring and to calculate the number of turns required for the spring for required loading condition. See here, this is a diagram. In this diagram you can see this is a spring which is loaded by load W. This is the normal nomenclature as already we have discussed with you. See here, due to loading, spring will going to deflect and deflection is known by delta. So delta is the deflection. So deflection we can find out with the help of this equation. That is delta will be equal to theta. That is angle of twist. When spring is going to deflect, it will going to twist. It's very important. So theta multiply by d by 2. D is equal to mean coil diameter of the spring. So this is main and important equation of deflection. I have given name equation number 1. So this is the deflection equation. So we can see here capital D is equal to mean coil diameter, N is equal to number of active turn, L is equal to length of the spring, delta is equal to deflection, theta is equal to angle of twist, J is equal to polar modulus, C is equal to spring index, G is equal to modulus of rigidity, D is equal to diameter of the coil, and W is equal to load, tau is equal to shear stress. So this is the deflection equation, and in this equation you can clearly see here is the theta, and as we know spring is going to deflect due to load W. So torsion equation plays very important role. So everybody must know torsion equation, that is Tj is equal to G theta by L. In this equation, this is a torsion equation, and in this equation we have value of theta. So how to find out value of theta here? So theta will be, by rearranging the term, theta will be equal to T into L divided by Gj. So this is equation number 2. So here in this equation you can clearly see this is a twisting moment. When load is going to act on the spring, it will going to twist. So twisting moment or torque will be, yesterday we discussed, that is W multiplied by perpendicular distance, that is capital D by 2, which is known as mean coil diameter. So here I am going to put equation number 3. Again here we require length of the spring. So here spring is a helical compression spring and one turn is a circular turn. So to find out the length of the spring, length of spring will be equal to pi d. Pi d is equal to circumference of one turn, but we have number of turns. So length will be equal to pi d into n. So here I am going to put equation number 4. So after this, J is equal to polar modulus, and it can be find out for the circular section pi by 32 multiplied by d raised to 4. So this is equation number 5. So we have value of T, value of L, value of J, and again put all these equations, all these values, means T, L, J in theta equation. So value of theta will be equal to T. So value of W will be equal to, T will be equal to W multiplied by D by 2. Length we have this value pi D into N divided by G as it is, which is known as modulus of rigidity, and J is equal to pi by 32 multiplied by d raised to 4. So after doing simplification here, 16 pi will get cancelled. So value of theta will be equal to, see here, value of theta will be, final value of theta will be equal to 16 W dt, it will be d square into n divided by g d raised to 4, and this is equation number 6. So now we have value of this theta, and initially we have this deflection equation, and deflection equation is delta is equal to theta multiplied by d by 2, and after doing all this calculation, we have value of theta, and final theta value we can put in this equation number 1. So delta will be equal to, delta is equal to theta multiplied by d by 2. Put this value of theta 16 w d square n divided by g d raised to 4 multiplied by d by 2. So again we have to do the simplification. See here will 8, here it will be d cube. So final deflection in the helical compression spring, we are at the end of this lecture. So deflection will be 8 w d and d square and d, it will be d cube n divided by g d raised to 4. So this is the deflection equation for the spring, and as we know, spring index C is equal to capital D by small d, and here we have d cube divided by capital D cube divided by d raised to 4. So instead of this we can put spring index. So same equation can be written as deflection for the helical compression spring in terms of spring index. It will be 8 w c cube n, and here what remain? G d, only g and d will going to remain. So this is the final equation in terms of spring index. You can write this equation in the final exam also. This is again important one. Up to here, hope you understand this concept to find out deflection in the helical compression spring, which plays very important role while designing the spring, especially for calculating the number of turns, which is very important to calculate the design of spring. So here again one more point is going to remain, which is end point. In some exams, deflection per unit turn is to be find out. So we can easily find out deflection. See here, deflection per unit turn can be find out. Deflection per unit turn. So n will be come over here. So deflection per unit turn will be 8 w c cube divided by g d. This is what deflection per unit turn. So that's all for this lecture. Hope you understand this very important concept of design of helical compression spring. Thank you for watching this video. In upcoming lecture we are going to take problem on helical compression spring. So be in touch.